Good morning, my dear students. Myself Sachin. I am continuing the topic composite section that is from module 1. And this one is our last topic to be discussed in the module 1. So in this session, we will discuss about the composite section. What do you mean by composite section? And what are the stresses developed in composite section? What are the strains developed in composite section? And what do you mean by volumetric strain? These are the main important parameters needs to be discussed. So as per the my knowledge, composite section, as the name indicates, composite. So till now we have discussed only one type of the materials or single type of material. So as the name indicates composite, here there will be more than two or more materials. A composite made of more than one material designed to resist the applied load, which is called as a composite section. Best example for composite section is RCC, reinforced cement concrete. So cement concrete is a type of the material. In that material, concrete will be the main predominant load taking carrying capacity of the member, and one more will be reinforced, that is steel. Combination of the steel as well as an RCC members, concrete members, both together we can call it as an RCC members. So whenever the load applied on the concrete, automatically steel will also takes the load, concrete will also takes the load, but we need to decide which member should take more load, which member should take minimum load, and which should be tensile load and which should be compression load. In detail we can study. So in a composite section, materials are placed in parallel and under the load sections behaves like a single material. Under the load, there will not be separation of materials. Of composite sections undergo equal amount of deformations. So whenever we are considering two types of the loads, best example I have already told, RCC. In RCC, while discussing the steel as well as the concrete, we should consider both deformations, whether it will undergo deformations under the load or not. Example, a section of reinforced cement concrete is made up of the material, two materials, that is namely concrete and steel. So in such cases, that load carrying capacity of a composite section will be P is equals to P1, P2, P3. That is nothing but an applied load. Applied load on the concrete. P1, P2, P3. If we are considering three types of the loads, automatically different materials of composite section should undergo different deformation, that is delta 1, delta 2, delta 3, because whenever there are different kind of material, so there will be different kinds of deformations automatically. So in such cases, whenever there is a different kinds of material, we need to consider different types of deformations. The material can also have a same strain if the materials are same length. And note this point, the material can also have the same strain if the materials are same length. So while discussing the problem, when we are considering the two materials simultaneously, that is a composite material, if the strain applied on the material, that is nothing but a strain deformation will be same whenever the length of the materials are same. And the next one, modular ratio. So modular ratio is a constant which, as the name indicates, ratio, which is a ratio between the two materials of Young's modulus. Suppose we are considering the two Young's modulus, one Young's modulus for wood, another Young's modulus for steel. When we are comparing the Young's modulus of wood and steel, in modular ratio will be there. For example, here I am considering modular ratio for steel and concrete is 15. That is, ratio modular ratio can be defined as ratio of modulus of elasticity of steel to the ratio of modulus of elasticity of concrete. So ES divided by EC, that will be 15, because we know the value of ES is 2 into 10 to the power 5 Newton per mm square. EC may be 9 or 1.2 into 10 to the power 5 Newton per mm square. So in such cases, the modular ratio will be different for different materials. In the examination, they may be asked, what do you mean by modular ratio? Modular ratio is a ratio of two different materials of Young's modulus. So whenever the two Young's modulus are considering, so in such cases modular ratio will be different. So next one is Poisson's ratio, again which is a constant. What do you mean by Poisson's ratio? As I already told in the previous class, considering in any engineering problems, the elongation of a tensile load along the applied direction, the length will be increased. At a same time, the width of the material has been decreased. So you can see here in this figure, a material. A load is applying left as well as right side. We are applying a tensile load. So we are applying a tensile load. Automatically, the length of the metal has to be increased. In such cases, whenever the length of the material increased, at the same time the width of the material has been decreased. So this type of the phenomena is called as a Poisson's ratio. Means in one direction, the length of the material has been increased. In another direction, the length of the material has been decreased. Both happened in the same time. This is known as a Poisson's ratio. If you want a textbook definition, the P, force applied in the direction, accompanied the contraction in the transverse direction. Considered AB, the length L is showing in the as shown in the figure, subjected to load P. Due to the tensile load, the bar elongates. So here the initial length was L. Whenever we apply a tensile load, the length of the bar has been increased to L plus delta L. So you can see here initial length of the bar was here. After application of load, the length of the bar has been moved from here to here. So the length will be increased L plus delta L. Delta L is nothing but deformation. Deformation along which direction? X direction. So when you are considering X direction, at the same time, the deformation from here to here, you can see here in length was increased from here to here, right? At the same time, the width was decreased, this portion. So at the same time, length has been increased and width has been decreased. This type of the phenomenon is called as an Poisson's ratio. So if you want a textbook definitions, you can call this as an lateral strain to the linear strain or longitudinal strain to the. So whenever the longitudinal strain is along a lengthwise, so you can see here the width of the section has been decreased. The initial width was B and which is reduced to B minus delta B. Initially it was B, now it has been reduced to B minus delta B. Simultaneously the depth D has been decreased. So we can easily say that the length has been increased only along one direction, but at the same time y and z directions have been reduced. This type of phenomenon is known as a Poisson's ratio. So the change in the length, which is delta L along the breadth minus delta B. Along the length delta L, change in the breadth delta B. So at the same time, what about depth? Depth is also decreased. So mathematically, Poisson's ratio is defined as ratio between lateral strain to the longitudinal strain. So longitudinal strain is always lengthwise, lateral strain is always widthwise. So lateral strain by linear strain or lateral strain by longitudinal strain. That's why Poisson's ratio is denoted by mu or 1 over m. This is already discussed in the previous videos for lecturing only. So if we wanted to define Poisson's ratio, epsilon b divided by epsilon L. What do you mean by epsilon b? Strain along width. Epsilon L means strain along length. So epsilon b, change in length, change in width to the original width. Epsilon L, change in length to the original length. So totally there are four dimensions. One is original width to the change in width, original length to the change in length. So Poisson's ratio can be defined as lateral strain to the longitudinal strain. So in the same case, whenever there is a change in width as well as a length, One more criteria, one more definition is there, that is constant volumetric strain. What do you mean by volumetric strain? Assume we have a one sponge. Whenever we sponge, I applied the load on both three dimensions, automatically the sponge gets squeezed. Or you can take a cloth, dry cloth. Whenever dry cloth has been immersed in a water, that will be shrink. That is nothing but the volume of the cloth has been changed. Similarly, for a sponge, the volume has been modified. So, volumetric strain defined as change in ratio or a ratio of change in volume to the original volume. Original volume can be defined as V, capital V. Change in volume can be defined as delta V, or you can call it as an dV. Volumetric strain is also similar to the strain only. In strain, what we have discussed is the change in length to the original length, but in volumetric, completely volume depends on volume. So here change in volume will happens. So change in volume to the original volume, you can call it as a volumetric strain. Best example for volumetric strain is your dry cloth. Whenever you immerse a dry cloth in a water, automatically it will get shrink. Whenever we are exposed to whether air or sunlight, automatically it gets original volume. So volumetric strain is a dimensional quantity. Why which is a dimensional quantity? Volumetric strain is similar to the strain only. That's why whenever the word strain comes, you keep that in mind, change it to the original. That's it. If the line along the lengthwise, change in length by original length. If the widthwise, change in width to the original width. In case of volume, that is nothing but length, breadth, height, both trace we are together we are considering. Volumetric strain can be defined as change in volume to the original volume. So volumetric strain is a dimensional quantity because here delta V mm cube, kilometer cube or meter cube, centimeter cube are divided by V volume, mm cube, kilometer cube, centimeter cube or meter cube. It will get cancelled. So you can see here, to show the volumetric strain of a rectangular block material, algebraic sum of the strain along three mutual perpendicular directions. So here I am considering x direction, y direction and z direction. And along the x direction, the length of the block has been considered as a L. Along the y direction, the height is h, and along the z direction, width is b. So whenever strain, volumetric strain should happen, the length should be changed. It may be increased or it may be decreased. Don't worry about it. Similarly, the width should be changed. It may be increased or it may be decreased. Similarly, height. So let us see. Let us consider a rectangular block of material dimensions L into B into H, length into breadth into height as shown in the figure. The initial volume was B, initial volume L into B into H, that is in terms of capital. That's nothing but a original volume. Final volume means after the application of the load, irrespective of type of loading, just consider after the application of the load, final volume, the volume has been changed, V plus delta V, that may be increased or that may be decreased irrespective of that. So volume has been changed. Similarly, the length has been increased because V plus delta V, original volume to the change in volume. Similarly, length to the change in length, breadth to the change in breadth, height to the change in height. Whenever we are considering all three together, length, breadth, height, so change in volume can be easily defined as strain, volumetric strain is change in volume to the original volume. Now, change in volume can be defined as V plus delta V minus V because original volume was only V. Final volume is V plus delta V. The difference between these two will be change in volume. So it can be written as V plus delta V final volume. Initial volume was only V, so can be written V plus delta V minus V. Similarly, L plus delta L minus L. Next, B plus delta B minus B. H plus delta H minus H. So after neglecting the higher order, so multiply with all these three. Neglecting the higher order means delta D into delta B, delta B into delta H, like this. So change in volume will be volumetric strain EV. Change in volume can be written as delta V divided by V. So LB into DH, BH into DL, LH into DB. You can see here L and B, length and breadth are constant, only the height is changed. In this term, breadth and height is constant, length has been changed. In this term, length and height is fixed, but width is changed. So whole divided by original volume, that is LBH. So whenever we need to make it as a separate terms, LBDH divided by LBH, BHDL divided by LBH, LHDB LBH. So BH get cancelled. The remaining term is delta L divided by L. Next come to the second one, LHDB divided by LBH. L get cancelled, HH get cancelled. The remaining term is delta B divided by B. And the last term LBDH divided by LBH. LL get cancelled, BB get cancelled. The remaining term is delta H by H. So just consider this term only. Delta L by L, nothing but strain along length. Delta B by B or D by dB by B, strain along width. DH by H, strain along height. So these three are the different strains along in a respective direction, along X, along Y, along Z. Whenever we are considering all three together, that will be change in whole volume. So you can written volumetric strain can be written as strain along x direction, strain along y direction, strain along z direction. So this is known as an volumetric strain. Next one small derivation likely to be asked in the examination. Show that the volumetric strain of cylinder is given by algebraic sum of strain along the length and twice the strain along the diameter. So strain along the length will be equals to the twice the strain along diameter. So when this is only applicable for circular, nothing but rectangular. Let us consider the length of the cylinder is L and the diameter of the cylinder is D. So usually how you will calculate the volume? Area into height. So here, because of the circular cross-sectional area formula is pi d square by 4 and the length is L. So total volume can be written as V is equals to area into height. Area is pi d square by 4 into height is L. So the total volume will be area into height, pi d square by 4 into L. So now differentiating dV is equals to, so pi d square by 4, usually d will be remaining, pi by 4 can be taken outside, d square into dl plus L into 2d into 2d, sorry, d into d. So EV can be written as delta V by V. Nothing but volumetric strain is change in volume to the original volume. This d square into dl plus L into 2d into dd, that can be written as divided by d square into L. So d square get cancelled, L get cancelled. The remaining term is dl divided by L plus 2dd divided by d. So if you wanted to write it as separate terms, d square into dl whole divided by d square l. So here d square cancel. The remaining term is dl into, so dl divided by l. This one term separate. Next one, l into 2d into d capital D. So here capital D cancel, capital D cancel. The remaining term is 2dd divided by capital D. So you can write easily volumetric strain is equals to strain along the length plus 2 times the strain along the diameter. So EL, strain along the length, plus 2 times the strain along the diameter, is prove that volumetric strain of a cylinder is given by algebraic sum of both nothing but along x as well as y. So algebraic sum of strain along the length, that is nothing but dl by l or epsilon l, and twice the strain along the diameter. So strain along the length plus strain along the diameter plus strain along the diameter. So volumetric strain can be written as strain along the length plus twice the strain along the diameter. Okay. Next, to show the volumetric strain of a sphere is the thrice the strain along the diameter. So this one is I'm giving as an assignment question to show. You can refer in textbook to show the volumetric strain of a sphere is the thrice the strain along the diameter. So in the previous we have discussed the only rectangular bar. Here we are considering as a sphere. If you want, you can have a glance, but you need to solve and the submit in a Google Classroom. Okay, thank you. If you have any doubts, please ask me, or I will only complete this. It's just simple. So d is in diameter of the sphere. Strain along the all three direction. That is nothing but, here I am considering an peripheral pi r cube divided by 4r by 3 pi. Nothing but pi by 6 into d cube. So volumetric strain is change in volume to the original volume. Original volume was 4 by 3 pi r cube. So change in volume is pi by 6 d square into dd, small d into capital D. So if you, while solving, you will get a 3 times of volumetric strain along the diameter. So if you have any doubts, please ask me. So this completes your composite sections. Okay, I will continue in the next class.